The chemical shift is the numbers that are on the x-axis. Sometimes we'll also call them parts per million, ppm. And so here we're given an unknown spectrum, and just notice that each of these signals has a different chemical shift. So there are correlation tables, just like there are for IR, where you can look up the chemical shift and see if what you would expect to find at around 1 or at 3.2 or so, or 3.7 or at 3.8. And so you can look that up in tables to help you figure out what the structure of the molecule is. Right, so what happens is that the proton types vary from one another because their nuclei experience a magnetic field that is not quite the same as the field that we apply. So here's the field that we apply. And so what happens is the nucleus is surrounded by an electron field, right? It's surrounded by the electrons. And so it's actually shielded. In other words, it's, well, think of the term shield, like it's like a shield that protects the proton a little bit from the magnetic field. And because of that, it doesn't take quite so much energy to spin flip from a parallel to anti-parallel spin state. Now, on the other hand, if you have a molecule that has had the electron density removed, we call it de-shielded from around the proton, then the proton feels more of the magnetic field. And so it actually takes more energy to do the spin flip, and so it ends up being downfield. Okay, and so when we have shielded molecules, the ones that have lots and lots of electron density around their protons, then it's going to be upfield, and de-shielded is downfield. Okay, so the two things that determine the degree of shielding, whether a signal is upfield or downfield, has to do with inductive effects, and then this thing called anisotropy, which you probably haven't heard of yet, but I'll introduce it here anyway. Okay, so what happens when you have inductive effects? That's like having a chlorine sigma bonded to your carbon, which is sigma bonded to your hydrogen, and what happens then is this chlorine will pull electron density away from the proton, and so it de-shields it by having that chlorine there. And so if we have more electron withdrawing groups, like oxygen or fluorine or what have you, those are going to pull the electron density away. And the more or the stronger the electron withdrawing group is, the better it pulls that electron density away. So the inductive effects are additive. So the more chlorines you have, here we have more chlorines, and they are, each of them is pulling electron density away. So you're getting de-shielding each time, and so each time that signal is shifting. So TMS, that tetramethylsilane that we use as a reference, it's found at 0 because the silane part here, the silicone, is actually donating electron density to the carbon and to the hydrogen. So it's making it really shielded. And so we see that at around 0, or at 0 parts per million, because that's what we define as 0. Anisotropy is what happens when you have aromatic rings and double bonds and triple bonds in a magnetic field. And what happens is the electrons actually start to kind of move around in that magnetic field, which, depending on, they add, in all of these cases, they actually add to the magnetic field. And so you end up needing a bit more energy to get those protons to switch from the parallel to the anti-parallel spin state.